Well, let's get started. Good morning, everyone. Welcome. My name is Jason Yang. I'm the dev lead of the Windows Analysis Technologies team. Today, we'll talk about code analysis. In fact, you're the first group outside of Microsoft who get to see these new features in Visual Studio 11. And today, we have a lot of exciting stuff to share with you. So let's get started.
Oh, yeah, and my name is Vince Smith. I'm the program manager for the Windows Analysis Technologies team. And today we'll be talking about primarily C++. So I want to give it, we had a few questions just when I was walking around. So I want to make sure everyone understands we won't be talking about FXCOP or any JavaScript or anything like that. So it'll be all C++ today. So 9 a.m. C++. Yay! First thing in the morning. So, and how this will work is I'll spend the first half of the talk going over the benefits of code analysis for C++. And then we'll go through and demo some of the great new things we've done in Visual Studio 11. And in the second half of the talk, Jason will go over how you can get the most out of code analysis by leveraging our source code annotation language. So there's basically three things we want you to come away with today. And that's that code analysis finds bugs early in development when they're cheap and easy to fix. Code analysis can often find bugs missed by traditional testing techniques like functional testing in particular. And that with some of the great improvements we've made in Visual Studio 11, code analysis is actually really simple and easy to use. So this is a quote down here at the bottom from John Carmack. Does anybody know who John Carmack is? Wonderful. Just a couple of you. So perfect. So yeah, so if you don't know, John Carmack is one of the co-founders of id Software. So they've produced games like Quake, like he produced the engine for Half-Life, for these kinds of things. So they've done a lot of really, really great work in the games environment. And at QuakeCon a few weeks back, John Carmack spent a considerable amount of time talking about his experience with code analysis and all the benefit he found in using it. So you can imagine, like, for Jason and I, it was like the coolest thing ever, right? To hear John Carmack talk about how great he thinks code analysis is. So it was very exciting. And I should also say that, like we said, we're from Windows, and within Microsoft, we take code analysis very, very seriously. So every product that ships out of Microsoft, it's a requirement to run code analysis. So this is Windows, Office, SQL Server, Visual Studio. We take it very, very seriously. And in fact, our team is responsible for the code analysis effort within Windows. So a lot of the improvements and innovation that has gone into Visual Studio 11 has been directly from our work in analyzing the Windows code base, which is massive. So let's move on to what's important for any project, and that's really quality. So I'd like to talk about this first real quick. And great customer experiences start with quality. I mean, we often define high-quality applications by what they don't do. So these are things like crashes and hangs, security vulnerabilities, poor performance. So these are characteristics of poor quality applications. So the interesting thing about these kinds of bugs is that no matter how innovative or useful or exciting your new application is, whether it's a desktop-based application or a new Metro-style application, that if you have these kinds of bugs, these are things that will keep people from installing and using your software, right? And likely tell other people not to use your software as well. So it's really important that we find and fix these kinds of bugs. The problem with that is that these bugs can often be really, really difficult to find and catch. And sometimes it's really easy, right? You click the button and your app crashes, right? Wonderful. But more often than not, it's timing related. Or maybe you have crashes in your exception handling code. Or maybe you just have to jump through the right set of hoops in order to find that one particular crashing bug. And with a potential customer base of 400 million people, those kinds of bugs, if you don't find them, or if you find them maybe once or twice in your development, you know people are going to hit those out in the wild. So it's really critical that we get those fixed. So this is where code analysis is really, really beneficial. Because code analysis finds bugs at compile time. So how this works is it's actually a special version of the compiler, and it looks for bug patterns in your source code. So what that means is that you're finding these very, very early before you spend all that time writing test cases and doing your functional testing, or whether you're debugging, and if you've ever had the pleasure of debugging an intermittent crash and having to track something like that down, you know that it can be a lot of work in a real time sink. So with code analysis, you find these very early, and at the same time, because it's a systematic way of finding bugs, it's very predictable. So rather than looking for the symptom, say the crash, or hopefully not, but like say the security vulnerability, with code analysis, you're looking at the pattern in the source code. So you're looking for the cause of the crash. You're looking for the null pointer to reference, or the buffer overrun, or when you're using an uninitialized variable. So with that said, though, that code analysis is not some end-all, be-all, right? It's not going to replace your traditional testing. You can really think of it as a complementary technique, right? It's something it's another tool in your toolbox to supplement your functional testing. So with that, let's go to a quick demo. Now, you guys have all been waiting for this. This is where it actually gets interesting. So what we have here is an application called Easy Investor. This is purely throwaway code, so we're not going to release any of this, but we'll have some other code samples out on the website, on our team blog page and whatnot for you to go look at. So what Jason just did is actually run code analysis. First thing you'll notice is code analysis is right here off the build menu. So how many people have used code analysis in Visual Studio 2010? Okay, so about half of you. Okay, so in Visual Studio 2010, first off, it only shipped in Ultimate. Okay, so here you can see that we're actually, oh, Jason.
So this is early release preview, right?
Uh-oh, did we have a crash?
Yeah.
Oh, no.
We'll restart. We'll make it work.
Okay. So yeah, this is pre-release. Of course, it's actually a demo. It's one of those demo gremlins because we've done this like probably 100 times, and of course, now when we run it for the demo, it finally crashes. So, do you want to flip it back over to the screen at least? Anyway, what you should have seen, we can kind of go over this real quick while Jason's setting this up again, is that code analysis now ships in Express. We have a subset of the most critical rules that ship in Express. And then all the rules, 200 plus, ship in Pro and Ultimate. Yay! So yeah, where that has come from is our philosophy that anything we can do to help make the ecosystem better and help make people who are writing Windows, particularly Windows apps, better. It's just overall goodness. So we want to get this out in front of as many people as possible. How are we doing, Jason? I'm going to flip back over here. Oh, is it working? Okay. I think it's working now. Okay, perfect. So the second thing you'll notice up on here now that's back is that it is just right off the build menu. So it's really easy, straightforward to find. You can just run it right there. And when you run code analysis, what you see now is on the side of the screen here is the code analysis diagnostics window. And this is where all your code analysis results will get put, and where you can actually go to interact with the code analysis engine. And if you remember how this worked in Visual Studio 2010 Ultimate, you got them just in the compiler error list window. So now that the code analysis is finished, Jason's going to click on the first warning here, the dereference null pointer. And what that gives him is some little more information about the warning. That he's dereferencing null pointer a price amount map. And what you see on the right, we call these key events. These are essentially, if Jason were to click on the first line in the code analysis window there, it actually tells him a little bit about what the analyzer is doing, right? And it maps that back to the line of code. So rather than just telling you, hey, you have a problem here, right, on this line, go ahead and try to figure out how we got there, right? We're actually going to walk you through how the analyzer found that problem. So what we have here, if Jason clicks more information, you actually get a little more information about that. So we can see that price amount map is null, and then we assume that the analyzer assumes that in the switch case, it resolves to case 3 here, chase case 1. Oh, yes, and then price amount map is dereference, which may still be null. It's still pre-release, guys. So Jason, being the skeptical developer that he is, doesn't trust every output from every tool. So he's going to go ahead and run this to see if he can catch this at runtime. So what we see here is, please don't follow our lead when it comes to UI design. Okay, we're code analysis. Okay, we're not the expression blend team. Okay, so Jason's going to click sell, and sure enough, right, we run into the exact same issue, right, at runtime here. This is the same dereferencing the null pointer that causes the crash in the app. So let's flip back over to the slides real quick. So we'll go into a little more demo here in a minute, but I just want to cover, before we go over all the other features, is kind of why we decided to make the improvements we did, and then what kind of guided that. When we started planning for Visual Studio 11, we went out and talked to a lot of people who use code analysis, and you use the existing version in 2010 Ultimate, and then a lot of our internal folks within Windows as well. And what we heard across the board, it was very clear that there's really 3 areas that people would like to see us improve. And that's really about making the analyzer more understandable, so that you can you know how the analyzer found the problem it did, and it can walk you through, so you can get to the answer, to the fix much faster. Second is about managing the number of results. So if you've run code analysis, particularly on a large code base, you can get inundated with results. So that was another big piece of feedback, was help you manage those sometimes large result sets and give you ways to prioritize and to filter in these things. And thirdly is about, of course, just improving the accuracy and the kinds of defects we find. And we strive for this every release. And like I said earlier, because we run these same tools internally, we get a lot of really good data and really good understanding and analysis just from running on a code base like Windows and like DevDiv and Visual Studio and these kinds of things. So with that, let's go over real quick the features we've done to help with those particular issues. So we're back in the Easy Investor app. And Jason, our Easy Investor developer, has made some changes to this Easy Investor app. And he's been working in the stock engine class. So he's really most interested in any warnings that have come out of the stock engine class, the work he's just been doing recently. So he's going to go ahead and filter using this bar up here, and that will give him just the warnings that exist that filter to match that keyword. So yay! So you can filter on class, you can filter on function, you can filter on file name, you can filter on warning number, or anything in the description of the warning. After Jason does this, he gets just these warnings that relate to the stock engine class here. So he's going to go ahead and walk through the first one. We're going to walk through 3 of the kind of the very common defects and the real critical defects that code analysis finds. Like I said, we find these are all issues we find in Express, and in Pro and Ultimate we find a lot more even. So what we see here is delay count is not initialized, right? It looks kind of obvious. And then the analyzer tells us that if it skips this loop by essentially assuming that transaction count is 0, then delay count is returned without ever being initialized. So these are kind of bugs that they may seem trivial, but we're all developers, right? And we all sort of make these kinds of mistakes. And that's kind of to get back to that point, that's where code analysis is really helpful, is finding these kind of mundane things that maybe, you're a little tired, it's 9 a.m., you're trying to, write a bunch of code like we are right now, and you miss some of these things. And so code analysis can help you find those so you can get back to writing the features or finding the really complicated bugs that take more manpower, take more brain power to do. Let's move on to the next one. So the write overrun. Here you see again, code analysis really does a clear job of explaining how it found the problem it did. So it walks you through that index receives the value of number of transactions, and that prices is an array of Talend elements because of that, and that if you enter this loop, what's happening here is you actually write to that 10th element of prices. And it's because Jason absentmindedly used index instead of I in his reference of this array here. So lastly, let's go over this dereferencing null pointer. And this is one that I really like to show because if you look through here, what ends up happening is this walks us through a loop, but the error only happens, the null pointer dereference only happens the second time through the loop. So the first time through the loop, delay transaction is false, and then when you go back through the loop again, now that delay transaction is false, we actually dereference, down at the bottom here, we dereference stock trade before ever having actually allocated it. So if you didn't have this kind of a view into what's going on, these are the kind of things where, and we got lots of feedback, particularly from internally and things like this, where these are the kind of things you'd have to hold on into in your head. You have to walk through the loop, remember all the state of everything, walk through the loop again in order to find that issue. So now it's much, much clearer in how the analyzer walked through and got to the place where it did. So lastly now, let's say that Jason has gone through this and he's looked and tried to understand and said basically, yeah, you know what, this will never happen, right? This is the 1 in a million times where the code analyzer is wrong and it's actually a false positive. Okay, we're going to assume. And because of that, Jason just wants this to go away. So what he can do is right down here under actions, he can hit actions and then just click suppress message in source. And what that does is that adds that pragma for him right there in his code. And now the next time he runs code analysis, this warning will never come back. So it's gone, right? Until he removes that pragma. So it's very simple, very easy. Just, yeah, you can get right through it. So the last feature I want to show is directed towards our enterprise customers. It's a feature that we've included in Pro and Ultimate, and it's the idea of rule sets. So if you're familiar with FXCOP, then you're already familiar with rule sets. But if you're not, what rule sets are is a way to, it's a configuration file where you can set what warnings the analyzer is going to show you. So this allows you as an organization to go through and set what's important for you and what you want your developers to see. So let's walk through that real quick. We'll create a new one of these. So here we go. In order to create a new rule set, Jason's going to click File, New, File, and then create a new code analysis rule set. And here he'll go under native, C++. And this is a list of all the warnings that code analysis will expose to you. So here you can pick things like dereference null pointer, uninitialized memory, things that are really important for his organization. And then he can actually choose the action that he wants to have happen when an instance of one of these is hit. So he can either make it an error and actually break his build, or he can just make it an informational warning. On top of that, Microsoft actually ships, or we ship, a few default rule sets. So Jason's going to go right-click on his project properties, and then under code analysis, he can open up the Microsoft native recommended rules. He can open this up, and then this is actually what we ship. This is the list we ship of out of the box what we recommend you run. So he can use this as a template to create what he thinks his organization needs for code analysis. So I think that's pretty much it for what I wanted to demo. So just to go back over kind of what we saw just now is for Visual Studio 11, we've added what we term key events. These are the things that highlight what the analyzer is assuming and walking you through that code, along with code step through, in order to help you better understand what the analyzer is assuming and how it found the problem that it did. And then secondly, we provided the keyword filtering and rule set support to help you better prioritize the rules you do get back from code analysis. And then thirdly, we've done a bunch of work around just improving the general accuracy of the analyzer, as well as the kinds of bugs that the analyzer finds. So with that, I'm going to turn it over to Jason, who's going to talk to you more about the kinds of bugs that the code analyzer finds, as well as how you can get the most out of code analysis by using our source code annotation language.
So what do you guys think so far? Yeah. Thank you. So over the last few years, the static analysis technology has really been improved immensely to a point that we at Microsoft are using that technology extensively for all major Microsoft products. So our mission is to make these state-of-the-art programming tools available to people like you to help you write more reliable and more secure applications. What Vince has just demonstrated are some of the ways you could use to interact with the analyzer using the rule set configuration or the key event diagnostic system. What I'm going to show you next is that you can actually interact with the analyzer in a much deeper way through source code annotations. Source code annotations are kind of similar to code comments, but a key difference is that annotations can be understood by both humans and analysis tools. So you can think of annotations as checkable comments. Or you could think of annotations as a compile time assert system. The Microsoft source code annotation language, or SAL, is a language that we designed to let you capture important aspects of the intent behind your code. I'm sure most of you have encountered this need in the past to talk about some properties that are really critical to the correctness of your program. For example, can a pointer be null? And if you need to initialize a parameter, whose responsibility is it to initialize that? Should that be the caller or the function being called? What is the size of the buffer? Or if you need to change a shared variable in the multi-threaded context, what is the lock that you need to hold? These are all critical programming properties that you need to think about if you want to design, implement, or use your API properly. Unfortunately, the existing language like C, C++ doesn't provide you this built-in support for specifying these properties. So in the past, what you have to do, you really have to rely on code comments or informal documentations. So here's the good news for you. With SAL, this is really a much better approach. What SAL gives you is essentially three key benefits. First, it's very consistent, so there's no ambiguity. And because tools can understand that, so they can work on your behalf to automatically catch violations. And finally, if you clarify all the contracts between the functions, then the analyzer is able to focus on one function at a time instead of trying to analyze the whole program altogether. So what that means to you is that you can receive your analysis results back very quickly, like what you have seen with the previous demos. So let's take a look at this example to see what cell looks like. In function print, we have a single cell annotation, in. So what in declares is that parameter p is a pointer pointing to an input element. It has been already initialized by the caller, so it's ready to be read from inside the function. In addition, the input cannot be null. So imagine if you're calling this function print by passing a null pointer, like what's shown on the left-hand side here, it's a bug because it will result in a null dereference. So if you see this warning popping up, there are two ways you could approach this. One is that you could change the implementation and the annotation of function print to make sure it can handle a null input properly. Another approach is to make sure that whenever you call this function, the caller has to make sure you don't pass in a null, as shown on the right-hand side here. So as you can see from this example, the contracts between these functions are really crucial, right? When you call a function, what is the obligation that the caller has to meet? This is called preconditions. And after a function returns, what has been done by that function? This is called postconditions. These are the sort of things that you really should be thinking about anyway when you design your code. But Cell really makes these implicit rules explicit. So Cell removes ambiguity. So for a bug like this, it really has no place to hide. And if you find any inconsistency, you can figure out whom to blame. So here's a classification of the common cell annotations for pointer parameters. If you have a pointer for an input parameter that has been initialized by the caller, you should use annotation in. If you have a pointer pointing to an output, which has not been initialized yet, and you're expecting this function to fill that in, then you should use annotation out. If the parameter provides both input and output, you use in-out. The annotation out pointer is very similar to the annotation out, except it's for a pointer to a pointer parameter. Another thing is that what you're looking at here, we're also showing that there are two flavors of these annotations. One is called required. The other is optional. Required means the input cannot be null, and optional means the input could be null. So if it's an input parameter, the callee, the function that taking that parameter, has to do enough null check to guard against null dereference. And these are what we call the composite annotations. They're actually a very concise set of annotations that are predefined based on a set of low-level primitive annotations. And in practice, when you start to add annotations to your code, you should try to use these predefined composite annotations as much as possible. And they should have covered the most common coding patterns already. So in this release, you will actually get the most dramatic upgrade in static analysis since Visual Studio 2005. In particular, the combination of a lightweight analyzer and the strong support of Cell provides a very unique and very powerful approach to help you push quality upstream. So what this approach accomplished is that it actually enabled Visual Studio 11 code analysis to accomplish 3 goals. The first one is around coverage. So the code analysis in Visual Studio can cover a large variety of defect patterns. If you are a user of Express, you get a subset of the critical rules out of the box. And if you are a user of Professional and above, you get more than 100 additional rules for different problem areas, such as concurrency. And if you are a device driver writer, you get even more support for driver-specific rules using the Windows Driver Kit. So as you can see, it covers a wide range of defect patterns. The second goal is around accuracy. So we were able to make improvement in the precision of the tool. And what that means to you is that now you can spend more time focusing on real defects and spend less time dealing with false warnings. Finally, it's about the speed. As I mentioned earlier, because you can clarify the contract and the analyzer is lightweight, you are able to run code analysis repeatedly during your development process to make sure you don't introduce new defects. And you can do that without significantly slowing down your build. So now you may ask the question, what if I'm working on a fresh code base without any annotations to begin with? Well, the good news is that if you don't have any annotations, the analyzer is still smart enough to find certain class of defect patterns right away. So you get the initial benefit out of the box. Now, if you are willing to learn Cell and add some annotations to your code, you will start getting some incremental benefits, because the more annotations you add, the better coverage you will receive. And if you really want to get the full benefit out of Visual Studio Code Analysis, then you should fully annotate your code. Like any relationship, the more you put in, the more you get. So at Microsoft, before we started Windows 8 development, we made a big bet on the Cell technology. So we worked across the division to improve the design of the Cell language. We also went to the vice president of Windows to ask for support for a Windows-wide annotation cleanup. And that has turned out to be a very, very worthwhile investment. We have 5,000 developers in Windows, right? As you can imagine, a tool like this can really help improve the quality of our product. And based on our telemetry data, we can observe that on a daily basis, a lot of defects have been fixed by our developers on their desktop, even before they check in their code. So with that, we'll go ahead and demonstrate how this process works.
Jason, actually, I have a quick question for you.
Sure.
I'll throw you a softball here. We're all C++ developers, so I'm curious, you mentioned that the high-level annotations, there's the composite annotations, this is in, out, out pointer, those kinds of things. Is there a header file or a place I can go to see what makes up those composite annotations?
So cell.h is your friend here. So if you're really curious about how these annotations are defined, check out cell.h. Another thing we'd like to point out is if you take a look at any Windows public headers, you will see that these headers have been extensively annotated. So you will see these annotations all over the place. And in Windows itself, to date, people have added more than 3 million annotations. So you can, with Visual Studio, you get this tools that we are using at Microsoft, and you can actually leverage the huge investment we've already put in to make your app much better. So with that, let's go ahead and do a demo.
All right.
So
here we are.
Vince is working on a piece of code to manage his bank account. And he's about ready to do some manual testing. But before that, he would like to just run code analysis and see what he can find. So again, code analysis is right there from build, very easy to find. And one thing to notice here is that this is the code running in a multi-threaded environment. So we want to make sure we do the locking properly to make it thread safe. How many of you have been developing multi-threaded programs before? Wow, almost everybody. Yeah. So you must have experienced the pain about how hard it is to get it right. Now, with code analysis and Cell, it can really make it easier. So what we're showing now is that we're doing this analysis run without any existing annotations. But then we get a warning saying, hey, there's a failing to release lock problem in this particular function. And when we take a look, sure enough, we enter the critical section at the beginning of the function, and we check certain conditions. If it happens, we bail out without releasing the lock at the right place. So we'll go ahead and fix that problem by releasing the lock here. Even though this is a very simple example, it actually revealed a very common coding pattern. And if you forget to release a lock, it can easily lead to a deadlock if another thread is waiting for the same lock. So we'll run code analysis again, and hopefully it can be fixed. So very quickly, the results comes back, and sure enough, it's resolved. So the next thing we want to do is, we know this variable balance is very critical because Vince wants to make sure his balance always gets the right value. So we want to make sure whenever we change the value of balance, proper lock needs to be held. And in the past, this is actually very hard to accomplish. You don't have a formal way to check this. Now it becomes very simple. All we need to do is to add a single piece of annotation called guarded by. So Vince will go ahead and add that annotation. So what this says is that it declares the intent that the lock CS is going to be used to guard the access of the shared variable balance. And we'll go ahead and fire the analysis to see what's going to happen. So again, very quickly, the results comes back, and it reviews that there is a potential risk condition in this function, unsafe withdrawal, because we haven't acquired the lock properly yet. So what we showed you is that in a few minutes, you could actually use code analysis to discover some concurrency-related defects that would have been very, very hard and time-consuming to diagnose and debug. How cool is that?
That's pretty cool. I have to admit, that's pretty cool.
And also, we showed you that we started using the tool out of the box without any annotations. And the tool, the analyzer, is actually sophisticated enough to find certain class of defects out of the box. And as you start adding more annotations, you will get more coverage, and it will be able to find more issues for you.
Back to demo.
So to recap, there are really three key things you should take away. First, code analysis is very helpful for you because it finds defects early in your development process. And the sooner you find it, the cheaper it is to fix it. So if you really want to save your development cost and maintenance cost, use code analysis. Secondly, because the way it works, code analysis systematically traverses all the code paths in your program to look for bug patterns in a very rigorous way. It's very good at finding those issues in the corner cases that would easily be missed with the traditional testing approach. So if you want to make sure that you cover those cases, use code analysis because it's systematic and it's thorough. Last but not least, you've seen a lot of features we're now building into Visual Studio to help you use code analysis in a more intuitive way. You've seen the new key event-based diagnostic system to help you understand the key steps leading to the defect, helping you to understand why the problem is caused. And you have the way to filter, to configure your rule set so that you can really find the information that you're most interested in. It helps you prioritize your effort to make your code better. And we also showed you that with the improvement in the underlying analysis engine and the strong support for the new annotation language, you have a better and deeper way to make your code fundamentally better because now you can declare your intent. You can make those implicit rules and expectations explicit. That way, it really helps not only the code analysis tools, but also it helps your teammates, right? In the future, if somebody new are taking over your code, they can understand your assumptions and expectations. So in Visual Studio 11, when you start writing your Windows 8 applications, definitely try these new techniques you've learned today. That'll help you improve your code quality. And if you're interested, we have some related sessions that you should watch. And we also have a lot of MSDN documentations that you could read to get more information. And if you have feedbacks, we'd love to get your feedbacks. So send the feedback to us, and we believe we have made a lot of improvement in Visual Studio to help you make it easier to get your job done. And we all hope that you can get a lot of stars from your customers' reviews for your applications. And reliability is really a key factor here. And code analysis can help you reduce hangs and crashes, and that can really help you improve your reliability. So leverage that, try it, catch bugs before the bugs catch you. Thank you.
So if anyone has questions.
So yeah, with that, we can answer some questions. If you could use the microphones on the side, that would be great.
Yeah.
Yes, sir.
Is this analysis available for all dialects of C++, including legacy unmanaged stuff? Cool.
Yes.
Very well done. Thank
The
you.
answer is
Absolutely.
yes.
Yeah. That's our bread and butter.
Yes.
Regarding the SAL, has it been designed in such a way that it can be cleanly removed for when you're compiling with other tools, when your code is shared?
Right. There will be a version of SAL definition that basically will redefine all the macros to no-op. So if you intend to port your code to other platforms without SAL support, it's available. Yes?
We're in the process of building a 64-bit version of our app using our 32-bit code base. We have both supported at the same time. So we've had to use a tool called Viva 64 to help find errors like what you've got here. Is there any built-in support that it will continually monitor and look for 64-bit issues in your 32-bit code?
Do you want to address that?
So the question is, let me make sure I understand. Sorry, the question is essentially, will we support 64-bit in prefast, and will we in particular support finding issues of 64-bit code in 32-bit code where that becomes a problem?
Yeah,
Okay.
exactly.
So currently, prefast does not, or I'm sorry, the code analysis in Visual Studio 11, there's no support for 64-bit in this build right now, but it's one of our highest priorities, and we're really shooting for it as a goal for this release, and we're going to do everything we can. As far as finding those issues where 64-bit versus 32-bit, where that becomes a problem, I think we definitely have some support for that. If you follow up with us offline, if there's specific things you're looking for, we can either confirm that or take it back with us, okay. and look into what it would take to find issues like that.
Okay. Thanks.
Yeah.
Yes, sir.
In the lock not released example that you showed, is the tool smart enough to catch a lock not being released due to an exception being thrown? I haven't expected that to come up.
So the question is whether the analysis tools could handle situations when exception happens. So the answer to that is no, not quite yet. The analysis engine is capable of simulating a lot of the exception behavior, but for the tools you're getting with the release right now, it doesn't handle that yet.
Okay, will the guarded by syntax work if you're using wrapper classes on your locks?
Yes, it works.
Okay.
So the lock expression that you're using in these annotations are any legal in scope expressions. On this side.
I'm curious about what kind of tools you use internally to actually perform the source code annotation. Are you just doing things manually? Do you have some sort of tools that help in the process? And if so, what kind of tools could you release publicly?
So the question is what kind of tools and process we use at Microsoft to enforce the deployment of static analysis. Is that the question?
And also to automate, not automate it, but just make the process easier rather than just going in manually and text editing hundreds of files.
If you think about the opportunities you could apply a technology like code analysis, there are certain opportunities during the development cycle, right? There's the short loop, there's the bigger loop. The shortest loop is, you're working on your code, you're developing or implementing your function. This is what we call the desktop situation. So that's one opportunity you'll start to see code analysis coming in to help you find issues. And with Visual Studio 11, this is essentially what you guys are getting. When you write code, you will see the issue right there. At Microsoft, we have a system called OACR, and it's deployed for most of the divisions. What it does is it actually works on the desktop, on the background. And if you have introduced a bug that is detected by these tools, it'll just pop up and showing you that there's an issue. So that's the kind of the desktop scenario. And also another good place to enforce these tools is when you are ready to check in your code, right? So there are also some tools in the check-in process to help you find issues. And we also have like a very heavyweight, big hammer process. That is that whenever you're ready to reverse integrate your branch to your parent branch, that's where we have something called quality gates. And these gates are essentially the process you use to run these static tools to make sure that you haven't introduced new bugs, so that whenever you RI, you reverse integrate, all these issues have to be fixed
And-
before you can do that.
And to address your question directly around some sort of auto annotation tool, we don't currently right now. It's something that we've played around with, and we can understand kind of how that would look, though we don't really have anything yet. It's kind of we can talk about more offline, but it's an interesting problem of, do you interpret annotations based on how the program works today, or do you go back and do you really think about what is the intent of the person who wrote it, regardless of what the implementation says, right? So there's a fine balance you want to achieve with a tool like that.
Thank you.
Does that address your question?
Yes, definitely.
Okay.
Thank you.
Yes, sir.
Yes.
Yes. I'm assuming you can run all this from scripts, so you can automate the process of doing all this. And if so, would you use the filters to exclude certain parts of your code? For example, if I'm using the Boost library, and I don't really care about looking for problems with them, but I'm only concerned with my own code, could I exclude all those headers and everything?
It's a great question. And a great piece of feedback. Right now, all the filtering and the rule set support is done at the UI layer, but we'll take that back. That's actually very, very good feedback, and something we can certainly look into.
Because I've used PCLint in the past.
Yeah. Okay, yeah, thank you.
This looks really good. One of the issues I had with the way it used to work was I would run an analysis, double-click on a line, and go fix something, and then recompile to see if that fixed it, and then all my annotations were gone. All the results from the previous analyze disappear. Are the results of your analyze in that separate pane sticky? I mean, do they preserve?
Yeah.
I need a way to go through a whole set of them.
Yeah.
Without losing them. Can I save them
So
and bring
yeah, and the issue you're talking about is essentially that code analysis does a full recompile.
That's right.
Every time it runs. In what is released today, that's still the case. It's great feedback, and we're looking at ways to do more of a compilation unit style result sets where you would, just like you were saying, where you do a sticky thing. It's great feedback. We'll certainly take
and
that
maybe
back.
even, to me, it's just something like if I could just do a save and load, reload, save it. I do a build and then spread it out to the team. So.
There's definitely ways you can do it that way. If you want to follow me offline, and we can certainly post things like that on our blog and stuff on how you can get to the actual file. Thank you.
Yes.
Actually, two questions. The first one is, what's the FP rate on this, quote-unquote FP rate? And the second is, you mentioned there are telemetry on, savings from using this before you start building, start an actual test cycle. Can you share a little more information there?
I'm amazed that we got through so many questions before somebody finally asked, what's the accuracy rate? So that's great, but yeah. Jason, do you want to talk about that?
We certainly have done a lot of work to try to improve the precision of the analyzer. And one thing you learned with static analysis that, it is a challenging area that, in certain cases, you really have to make conservative assumptions about what the code is doing. So, I'd say it's inevitable to see false warnings or false positives, those warnings that are not really going to happen in reality. And on the other side of the coin, there's also the false negative, right? There is a bug, but the analyzer is missing that. So, we've made a lot of improvement to improve the precision, and I think it's very accurate, to a point that our developers are really using that on a daily basis.
Yeah.
But the false positive rate, that really depends on a lot of factors, like the size of your code, the nature of your code, your component size of the team. So it's kind of hard to use a single number to summarize that.
The short answer is it depends.
If you could share a set of common issues you typically miss RP against, at least we don't get a false of confidence, so we can run it. We can still manually go through things.
I recommend the best thing is to try it yourself and see how it
Exactly,
works.
and give us feedback on that.
Send us feedback.
Yeah, And I would love the write-up. It's something we obviously can't talk about in 1 hour and explain all the the intricacies and things like that. But I would love to do a write-up and something that people can read and get a better understanding of where the analyzer is more accurate, where it's less accurate, kind of the reasons why, and all that stuff. So yeah, it's something we would love to address, at least in a communication way. So thank you for bringing it up.
We'll open up our blog site, and if you have any questions, feedback, feel free.
Yeah.
And
We're a very small team,
follow up.
so we're excited to hear feedback from anyone.
Yes, sir.
Yes. So our team does use Subversion to check in our code, so we can't really enforce passing code analysis, on check-in. But what we can do is we have an automated build system, and we typically automatically build all the code, and what especially managers want is a report, right? A code analysis report. Is there support for generating a code analysis report from the command line, and something that they can look at and say, okay, today we had 10 problems, and next week we only have 5. You're kind of keeping people.
There's definitely, so there are ways to allow you to do that. So essentially, the code analysis engine outputs an XML file.
Okay.
That's of a schema that you can depend on.
Yeah,
so,
we can do anything with that.
And then you can certainly use that to go, write reports against.
All right, thank you.
Yep. Yes, sir.
So like in the compiler today, you can turn on warnings as errors. Is there a way to pass a switch to say analysis as errors?
Yes.
That's essentially what we showed in the demo. When you configure your own rule set, you can either select that as a warning or as a error. Right? If it's an error, it will break the build.
So by default, they're all just informational warnings because we don't want to ship a product and have everybody upgrade and all of a sudden their build breaks. But you could go in and change that either with a script or by hand, and then turn each individual warning or all the warnings as build breaking if you want. Yes, sir.
So given that we're talking about C++, are there any particular corners of the language that this just doesn't deal with well? Like traditionally, it's been very hard to static analyze virtual function calls, just even at all.
Yeah.
So,
I'll let Jason give the long answer. But when I hear the corners of C++, I always think of pretty much most of the language. It's like a giant corner case that it's powerful, but at the same time, it allows you to do things your own unique way, which presents obviously a challenge for any analysis tool. Right. Jason, do you want?
I would say by and large, the analyzer we're using does a very decent job in handling both C and C++. So again, try out the tools yourself and see how you like it.
And remember that we run these tools every day in Windows, and I don't know how many hundreds of millions of lines of code we have in Windows now, but we make the assumption, and it's an assumption, and we definitely don't rely on it completely. But we're confident that if you can run this in Windows, you see some really crazy stuff. Right?
We have certainly seen a lot of corner cases.
A lot of wow, that doesn't seem to be ISO standard.
Yes.
But whatever.
One more over there.
I thought the guarded by was interesting. Is there anything similar for atomic or interlocked or some lock-free techniques?
In the current release that you get, no, there's no support for atomicity analysis. If you are interested, you can follow up with me offline. We have a research paper published to talk about how you can do some of analysis about atomicity.
Thank you.
Yes.
Yes, sir.
Yeah, so I had a question on for instance, so this is a lot of code analysis, which is really great for finding issues in the code itself, but for instance, if you're looking at a requirement where you have a function, you want to check, it's a complicated function, you want to check that the result, between the pre and the post condition, there's a certain relationship, and that actually is what defines your function in the end and what you should be doing. So for instance, your output shouldn't be larger than 100. Is there a way of expressing that in Cell and having the static code analysis check on that?
We should probably follow up on this offline. So the SAL language is actually very, very expansive. So we showed just a small amount. And we have come up with a lot of very good ways to express invariance in detail. And you can think of it as there's a language that is SAL, and then there's the checkers, and those rely on SAL. But sometimes the language is typically out in front a little bit. Right. So while you can express some of those things in the language, there are certain things that you may or may not be able to check for quite yet in this version as far as a checker. But the idea is that if you try to start getting those invariants specified in the language, that as the tool set grows, we can continue to provide better and better results.
So we're actually running out of time. If you have more questions, you're welcome to come over and talk to us.
Yeah.
Thank you all very much.
Thank you. Appreciate it. Yeah.